for today. I will get this one posted sooner. Again, I was just so out of it Thursday, Friday. So what I want to do is resume what we were talking about nuclear physics. Matthew sent me some pretty cool stuff on nuclear fusion, which we can look at. Again, this is a really informal class, so I please ask me stuff. This is kind of an opportunity to talk about, you know, hey Jack, so you want to make a bomb? Now we're talking about making bombs, which I understand is one of his memes. Um, so we're going to talk about stuff like that, but we can also talk about fusion power, the use of nuclear reactions to in medicine, which was Danielle's topic. We can talk about travel using nuclear rockets if anyone wants to go there. So what I want to do is kind of review where we were last time, and me kind of try to make that a little bit more coherent because I was in not good shape before, and then kind of talk about um, kind of in tandem some issues in nuclear reactor engineering and nuclear weapons engineering, and then transition from there to wherever we want to. Does that sound good to everybody? Okay. So from before, what we saw were that some nuclei are unstable and decay. They decay into um, they decay by turning into another kind of nucleus that's basically their same size. Mm. They change into another nucleus, spitting out a small piece. But the really interesting thing is what happens when neutrons interact with other nuclei. And neutrons are really the key to this whole thing. Um, so, really, three things can happen. It can either bounce off, losing energy. That turns out to be important. It can um, be absorbed, which transmutes the struck nucleus. Um, so an example of that sort of reaction um, would be hydrogen 1 plus a neutron goes to hydrogen 2. Hydrogen 1 is just a proton. Hydrogen 2 is a proton and a neutron stuck together. So I can make heavy hydrogen this way. But the really exciting thing is that it can induce fission in susceptible nuclei. These are called fissile nuclei. Yeah. And there's a wonderful chart that I found of how likely these different things are for different nuclei. So here, cross section just means you can think of it as how likely something is to happen. It's cross section is it's got units in area, units of area. Cross section is kind of the target area for a reaction. Target area is kind of a weird phrase. Basically, it's um, if I imagine shooting neutrons at something, the reaction will happen if one of them comes within a certain target area of the thing you're shooting them at. But this is kind of averaged over probabilities. Really, one way to think of this, like it's got units of area just because those are its dimensions, but really it's a probability. It tells you how likely certain reactions are to happen. So I want to focus on a couple of the ones down at the bottom. So if you look at the ones under fuel, um, notice that uranium-235, oops, wrong tool. Uranium-235, this one is fissile. It's got a very, very large absorption cross-section for fission. So that is a huge number. That's the biggest number for fission. Notice that uranium-238 is not fissile. So U-238 doesn't fission. Notice that the cross sections, there are three things that can happen, either scattering, capture, or fission. Those are my examples. So another thing to note is that we have two different columns for this. The three on the left, so point that out for what a cross section is. Thermal here means slow neutrons, meaning that they are not going any faster than the random motions of atoms around them. And on the right, we have the cross sections for fast neutrons. So notice that, if we're talking about fission, that fast neutrons have a very, very hard time inducing fission. So a couple of other things to note here. Notice that the fission cross sections are low for fast neutrons. Nope, tool. But slow neutrons, thermal neutrons, do induce fission in slow neutrons do induce fission in U-235, but not in U-238. We'll talk about plutonium later, the bottom column. So if I want to make the other thing to note is that uranium-238 has a higher capture cross-section than a fission cross-section. So uranium-238 will actually absorb neutrons and turn into something else, which turns out to be plutonium, and that's interesting because, as you see, plutonium is also fissile. So I'll call that one out. And so we have here that uranium-235 is fissile from slow neutrons. So in order to make and it's a little bit fissile again for fast neutrons, right? Um, so put an arrow there. So in order to make a sustaining nuclear chain reaction, I need a large collection of fissile nuclei called a critical mass. Now, if you're making a nuclear bomb, you have no opportunity to slow down neutrons because a nuclear bomb does its work very, very quickly. Wrong tool. So in a bomb, because I know Jack is always interested in making bombs, right? I didn't know that was one of his jokes. So in a bomb, um, you need very pure 70% plus uranium-235, since all you have are fast neutrons. Remember, each fission produces fast neutrons. So you have a fissioning atom, 2.4 on average fast neutrons fly off. They hit other atoms, they induce those to fission, and so forth. But in a reactor, you can, it's called moderate these neutrons to slow them down. And notice that here, right, if we look at the fission cross sections, slow neutrons are 600 times more effective. So this is 600 times the cross section. So in a nuclear reactor, if all you're trying to do is make a sustaining chain reaction, you want to intermingle fissile atoms with atoms of some moderating material. So let's go back to the chart. I'm just going to stick it in here. Where is it? Here it is. Here's our chart again. We'll make it a little smaller. Doesn't need to be that big. So let's talk about good moderators. Notice that natural carbon is a super good moderator. So what's a good moderator? It's something with a high scattering cross-section, but a very low capture cross-section. So carbon is a good moderator. Oops, high scattering. I can't write. Low capture. Ordinary hydrogen, H1, here, it is an okay moderator. Because the capture cross-section is still pretty large. And again, please feel free to like type questions here if there's anything you want to talk about. Um, so the way you make a nuclear reactor, then, and I'm gonna pop in a diagram of one. Let's see. So here is a schematic of a nuclear reactor. This is of an RBMK type reactor, which is the same sort of the one as the one that blew up at Chernobyl. So there are a couple of pieces here. All of the steam and water lines, those are just to transport heat around. Notice that water is mostly made of hydrogen and oxygen. And notice that water here, H1, hydrogen is the main component of water, right? It is has some probability to capture neutrons, which is bad. Remember, capturing neutrons slows down the reaction. Scattering them actually speeds up the reaction because it moderates them. So, but in this sort of reactor, the water doesn't supply most of the moderation. We've got really, well, I'll talk about two types of reactors later. This is just an example. But what we're doing here, the carbon, the little gray things, you can see my mouse cursor, I think. Um, they absorb scatter the neutrons produced by fissions, slow them down, and then they'll find their way into another fuel rod and induce fission. So what might happen, right, in these fuel rods is a fission takes place, neutron comes out, it is slowed down in that moderator. I'll draw it as blue now. So it's been slowed down by the graphite moderator, goes over here, induces another fission. So 3 more neutrons come out. They are slowed down by the moderator, go over here, and induce more fissions. But what I've drawn here is a chain reaction that speeds up. And you don't want these things to speed up. You want it to be at a constant power. So these black rods that are drawn here, these control rods, these are made out of strong neutron absorbers. And by raising and lowering them into the core, you can, by affecting how many neutrons are absorbed, speed up or slow down the reaction. So a nuclear reactor is a balance between things that make the reaction speed up, which are moderation, the presence of graphite, and also can be the presence of water, and the things that make the reaction slow down, which are the control rods. So the way you make a nuclear reactor is you assemble a critical mass of uranium-235. You put it together, and this will create a exponentially increasing nuclear chain reaction. And then you move the control rods in and out to keep its power constant. So you're always balancing between speeding up and slowing down the reaction. Let me show you another diagram of a reactor. This is also an RBMK type. So this is actually Chernobyl when it exploded. So there are lots of colors here. I can get you the key for the colors in just one moment. Actually realized my YouTube recording was a little bit funny, so I'm fixing that. Stand by just one moment. So here Green are the control rods. Gray are the fuel rods. Um, these also contain water and graphite. Um, the red ones are computer-controlled control rods. Um, and the green ones are the manual control rods. And the numbers written inside the little squares are the distances that those control rods were inserted into the reactor core at the moment of the explosion. We actually have that data. And you'll notice the numbers are all pretty small. Um, many of them are zeros, which tells you that the operators of the reactor had removed the brakes on the reaction. We can talk about why they did that a little bit later, but spoiler alert, it was a bad idea. So this is kind of the layout of how you make a nuclear reactor. Um, this type of reactor had the control rods and um, the graphite moderator and the water that flowed over them kind of all mixed together. It was a particular type of engineering that the Soviets had done. But there's one other thing we need to talk about a nuclear reactor, and that is that when you have uranium, you don't just have uranium-235. So remember, natural uranium is 0.4% uranium-235 and 99.6% uranium-238. So that means that in a reactor, you have lots of uranium-238 around. So the next thing I want to talk about is what does the uranium-238 do in a reactor? Well, if you remember the chart from before, which I'm just going to pop in again. We don't need you to be that big. Whoop. Don't need to be that big. Go over there. Uranium-238 is, looking at the thermal cross-section on the left, right? It is something that will capture neutrons, but is not fissile. So the bad thing that uranium-238 does in a reactor is it absorbs neutrons. So this means to make a reactor with natural uranium, you need a very good moderator. Again, because all of the uranium-238 that's sitting around is eating a bunch of your neutrons, and if your moderator eats any more, then you are not able to have a sustaining chain reaction. So the very good moderators, there are two options. Those two options are graphite, again, high scattering and low capture, cross section, or even better, hydrogen 2. So, so here are your options for a super good moderator. Um, if you're trying to make a reactor that has enriched uranium, then you don't need such an efficient moderator. TK asks, what's considered high scattering? Because you're probably noticing that some of these other elements also have a high scattering cross section, right? Like iron 56. You're probably looking at oxygen, um, things like that, right? So there's one other thing I didn't mention about what makes a good moderator. Imagine that you have a very light object and you bounce it off of a very heavy object. It's not going to lose much energy, right? If you have an elastic collision. So if you shoot like a ping pong ball at a bowling ball, it's just going to bounce off, right? Um, so in order to have a good moderator, you also need very light nuclei. So hydrogen and carbon are considered as moderators just because um, their scattering cross section is high, their capture cross section is low, and they're really light nuclei. This is why hydrogen is even better than carbon, right? We can't use hydrogen 1 quite as well because its capture cross section is too high, but deuterium, hydrogen 2, is the best we've got because it's so light. As we get into these heavier elements, like you'll see zirconium 90. The problem with using zirconium is while it has this really desirable ratio of scattering to capture cross sections that you see there, it's too heavy. It turns out zirconium has a pretty high melting point, so we actually cover uranium fuel rods in a zirconium alloy as something that won't absorb neutrons and doesn't melt readily, but it's not a good moderator just because the atoms are too heavy. TK, does that answer your question? Ah, Grant, you're amazing. Yes. Um, Let me answer that question in just a minute. What happens to the moderators? That's an amazing question, and it actually has to do with uh, a couple of other interesting things. So, Yanju, in a natural uranium reactor, um, only the U-235 is fissile. So 99.6% of the uranium is not contributing to your chain reaction. It is just there. It's difficult to remove because remember, it's very difficult to separate atoms when, like, I give you a bucket of atoms and like 0.5% of those atoms are a fraction lighter than the rest. It's really hard to sort them. So if I just mine a bunch of uranium, it's really hard to pick out the ones that are best used in a nuclear reaction. Um, I'm stuck just having all of this U-238 around. But there's something else that the U-238 does. And this gets to Grant's point. We'll talk about the moderators in a minute, but an interesting thing, right? If U-238 absorbs neutrons, it's transmuted to uranium 239, which decays in 2 steps to plutonium 239. And plutonium is even more fissile, right? Plutonium has even higher fission cross sections for both slow and fast neutrons than uranium 235. So I have now two paths. Remember, to make a nuclear bomb, you need a whole lot of either very pure uranium 235 or very pure plutonium 239. And plutonium 239 is even better. So we've got two paths then to a nuclear bomb. Again, Jack is Jack in class always memeing about, like, so you want to make a bomb? Okay. I guess this is like a joke for him. Uh, so we have two paths to Jack making a bomb. And I'm just going to say, not really, right? Jack is not, he doesn't even do nuclear physics. So he's not, um, he's not someone who's going to go blow something up. He's just being funny. Um, okay. So no wonder Isabella's always asking about artillery. I'm having a little trouble with my stylus. Oh, it's good enough. You low key want to make a suitcase nuke. So TK, would you like me to talk about how to make a small nuclear bomb? Because I can do that too. I actually have a slide about it, or a picture about it. Um, so one of them is to um, sort the uranium 235 from the uranium 238. The other is, so this is called enrichment. The other thing you can do is make a reactor from natural unenriched uranium, and then uranium 238 will absorb neutrons and become plutonium 239. Now, since that's a different element, um, note that plutonium 239 is can be chemically separated. So that's easier. It turns out that in producing the first nuclear weapons, the United States did both of these at the same time. Both of them worked. So we investigated both enrichment and production of plutonium in a reactor, uh, and both of these methods led to functioning nuclear bombs. It turns out that plutonium is the preferred approach now, like now that people know how to do these things. You can also, um, since you can combine these in a nuclear reactor. So remember the note here that if you want to make a reactor out of natural uranium, you need a really, really good moderator. It turns out you can enrich the uranium a little bit, and then you don't need to be so aggressive in choosing only the best moderators. If you have a reactor that's burning slightly enriched uranium, you can use ordinary water as the moderator. And that simplifies the design and also makes it safer for a number of reasons. Um, and we can talk about reactor safety a bit after. I want to address Grant's question. Does this process degrade the moderators? So remember that going all the way back up to the top, when a neutron strikes a nucleus, there's some chance that it will be absorbed, right? We like our moderators not to absorb very many neutrons, but they absorb a few. And so when you say degrade moderator, what you really mean is it's going to turn some of the atoms in the moderator into something else. And those things are very often, it's a different chemical element, so it has different properties. And it is a different, they're often radioactive. So nuclear reactors make all of their components slightly radioactive over time because all of these neutrons flying every which way, some of them get absorbed. Notice that um, even if we're using the best moderator we've got, which is hydrogen 2, right, it's still got a small capture cross section. So in fact, even with the best moderator we've got, hydrogen 2, so deuterium, water made out of deuterium is called heavy water. That's why heavy water is interesting in nuclear reactions. Even if we're using that, some of that hydrogen 2 will turn into hydrogen 3, which is called tritium. Tritium is radioactive, and that's one of the types of radioactive pollution from nuclear power plants. Again, there's nuclear power plants are super safe and super clean. Like if I were living right next door to a nuclear power plant, knowing what I know, I would be super comfortable, super happy that I have emissions-free power, and also super happy that um, there would be, good jobs around me. So just to be completely clear, nuclear power plants are very, very safe. We've had a few bad accidents in history, but those are very small um, compared to the dangers of other sorts of power. But one of them is the production of tritium. Um, but Tigay, let me answer your question about fusion reactors, but I want to say something else about Grant's question because yeah, actually they've made the RBMKs a lot safer. Um, there are still like dozens of RBMK reactors operating in the Soviet Union right now. They're not the safest design. They were designed to produce a whole lot of power on the cheap. Remember, the reason they use so much graphite as their moderator is the Soviets didn't want to enrich uranium for their reactors because that's expensive. They wanted to run them on close to natural uranium. Um, so that meant they had to be really aggressive with moderation. And yes, Tigay, it does. Um, they don't even try to capture the stuff coming out of a coal plant. Um, in a reactor that uses water as its moderator, there's a built-in safety margin. Because if a water moderated reactor gets too hot, it's going to boil off its water. Even under pressure, that water will turn into steam, and steam is less dense than water. So if a water moderated reactor gets too hot and boils some of its coolant more quickly than it's supposed to, then the reaction rate goes down because it's lost its moderator. But in a graphite moderated reactor, the water is actually mostly contributing capture. Remember, water does both. Ordinary water, not heavy water, does both scattering and capture. So if the graphite, like in an RBMK reactor at Chernobyl, if that's doing most of the moderation, and then you boil off your water, you've actually sped up the reaction because you've taken out an absorber. So that's one of the inherent instabilities of these reactors, is their reliance on graphite for moderation so that if you lose your water, it actually speeds it up. Um, so Tige said, does that happen in fusion reactors as well? So this leads us into, believe it or not, your two questions about making a suitcase nuke and fusion reactions are related. Um, a fusion reaction produces quite a few super fast neutrons. So in these tables, when we talk about fast cross-section, this is the cross-section from neutrons produced by nuclear fission. Neutrons produced by nuclear fusion are even faster. And they have some chance to be captured, right? So in a nuclear fusion reactor, like a tokamak, the fusion is producing lots of fast neutrons, and those will be absorbed by whatever's surrounding the tokamak and transmute some of those atoms. So in building whatever's on the outside of a tokamak, you need to have something that can be bombarded by neutrons uh, without having its structural properties degrade or without getting too radioactive. And people have to think hard about that. Um, so we'll come back to suitcase nukes, but Grant had a question about degrading the moderators, which is a really good. There's a story associated with this. Um, so it's called the wind scale fire. Um, I'll just write it down here. So Windscale was a British reactor that was designed to produce plutonium and later, I believe, tritium for nuclear weapons. It was not designed to make power, so it was a low power plutonium 239 production reactor. Um, it didn't generate like I think it was tens of megawatts rather than a few gigawatts. And it was this sort of weird design where you pushed in little slugs of uranium containing, you know, U-235 and U-238. They would, you'd like literally push them in, and the reaction would happen. It would transmute some of the U-238 into plutonium-239, and then you'd push a new one in, and it would pop out the other. One would pop out the other side into a water channel. It would fall in the water. It was super hot at the time, and then someone would fish it out of the water and extract the plutonium. And this was just open to the air. It was air cooled rather than being water cooled, so there was no separate cooling loop. And what had happened was, so it was graphite moderated, and this goes to Grant's question about degrading the moderators. In such a low power, lowish temperature reactor, the graphite, every time one of those carbon atoms transmuted into another kind, so carbon is a structurally sound material, like it's a crystal of carbon atoms that, they form a regular pattern. And if you replace one of those carbon atoms with some other kind of atom, it messes up the crystal structure. And that messed up crystal structure accumulates potential energy. And over time, that potential energy, if it builds up too much, can be released all at once as the crystal kind of snaps back to its original structure. And so they would have to, in a controlled way, every once in a while, like cycle the temperature up and down to, it's called Wigner energy associated with these dislocations in the graphite crystal structure. And they'd have to, almost like annealing a metal, they'd have to anneal the graphite to get the Wigner energy out before it all came out all at once. But they messed this up at one point, and a bunch of that energy popped out when they weren't expecting and caught the graphite on fire because, oh, by the way, you know how coal burns in air? Graphite burns in air too because it's just carbon. So their moderator caught on fire. And this was it was in the 1950s, and this was at the time the biggest nuclear accident that had happened in the world. There was a reactor on fire, literally open to the air, and the stories are kind of chilling. Like there was a big tower above it, and somebody had insisted on putting in filters at the top of this big chimney in case something went wrong. Thank the gods they were there. But the lead engineer had to climb up the chimney on a ladder and like look down at this flaming core of the reactor, Um, and they finally wound up. They tried to blow the fire out with these big fans, and of course that just fed it more oxygen. And you've got a nuclear reactor on fire. It's spewing out pieces of itself, all of these fission byproducts that are radioactive. And eventually they got the idea of, okay, let's just like try to close off all the air and smother it, and that finally put out the fire. So yeah, that was a bad nuclear accident. And yes, so granted, it does degrade the moderators. Um, Yanju asks, can seawater replace the water as the moderator? Well, seawater has all kinds of stuff in it, and um, you don't want any of these elements that are very strong neutron absorbers. So notice that in these absorbers, boron is a really, really strong absorber. Cadmium and xenon can be profoundly strong absorbers. So if you're using seawater, um, then seawater would have the potential of absorbing neutrons. But what you can do is you can use, yes, a pure thing is easy to control the process. And when they were trying to build the first nuclear reactor in Chicago, um, the Enrico Fermi and that team called up like a company that made graphite, and they said like, we need ultra pure graphite, because the problem is graphite in the normal processes contains boron. And they said, we need some ultra pure graphite. We're not going to tell you why we want it, but I know that nobody else has ever cared about this before, but we need you to get all the boron out. And they're like, okay, whatever. Must be something for the war. And it was. Um, but, Yanju, water has a really annoying property, which is its tendency to boil at atmospheric pressure. So if you're trying to have really hot water, you have to keep it under really high pressure. And really high pressure things tend to, explode if you release the pressure. So some reactors, rather than using water as the coolant, use molten salt. You can also use molten salt as a moderator as well. And the advantage that these salts have is they're not going to boil even at atmospheric pressure at high temperature. And this is actually used in a lot of Soviet naval reactors. They use either molten sodium or I think sometimes even molten lead as their coolant, because these molten metals transport heat really well, so you don't need as much coolant. It doesn't need to move as fast, which is good if you're trying to keep a submarine reactor quiet. Um, and they're safer because they don't explode at atmospheric pressure. Um, Back to Tige's question about suitcase nukes and fusion reactors. So the Tige's first observation about fusion reactors is that nuclear fusion, also produces um, neutrons. There's a glitch in this picture. This word is tritium. Oh, come on, stylus. Ah! Sorry, my program crashed. Let's get it back. I have to click on a few things here. So, nuclear fusion requires super high temperatures, as we've discussed. So, it's very difficult to get those super high temperatures on Earth. Really, the only way to do it in a reliable way is inside a nuclear explosion. Again, this word is tritium. But if you're trying to make a nuclear explosion, again, you need a critical mass of plutonium. I need that room. So here is how you make a modern nuclear weapon. Um, you have explosives that compress plutonium. So plutonium-239 is fissile. Beryllium is a neutron reflector. That, yes, it's an accelerant in that it reflects the neutrons back into the plutonium. So this reduces the critical mass because you get some neutrons that would otherwise escape go back in. The explosives, the high explosives that you see labeled here, these are just here to compress the plutonium. But this blob of tritium and deuterium here in the middle, as soon as, yes, critical mass is dependent on the amount of neutrons. Remember, critical mass is the amount of a fissile substance, so that when you have a fission, um, you on average get at least one more fission from those neutrons. So if you only have a little bit of plutonium, one fission is going to produce, 2 to 3 more neutrons, but most of them will escape. But if you have a lot of plutonium, then more of those neutrons will encounter another plutonium atom before they escape. But if escape then makes a reaction harder to sustain, you can prevent the neutrons from escaping by putting something that tends to reflect neutrons around your plutonium. So they do that, and then at the core of the whole thing, they put a mix of tritium and deuterium. This is nuclear fusion material. So this is the sun, as you know, fuses ordinary hydrogen, but it turns out at lower temperatures, or lower pressures, you can fuse the heavier isotopes of hydrogen. So tritium and deuterium is fusion fuel. And it turns out that this fusion fuel is not actually producing much energy compared to the fission of plutonium. Exactly, Tigay. The fusion here is only to make more neutrons. This is not a thermonuclear bomb. This is how do we get an efficient fission explosion that's as small as possible. So you have this combination of fission and fusion to extract energy more efficiently from the fission. We do this in fusion reactors too. So nuclear fusion, right now we can't make sustained power from it, but there's a possibility we will in the future. And there are lots of people working very, very hard on it. And one of the ways that you can do that is you have so we can make controlled nuclear fusion in the lab right now in a device called a tokamak that confines hydrogen at millions of degrees in a plasma. The problem is it takes more energy to heat the hydrogen than you get out with fusion. We aren't able to net produce energy yet. But when we get to that step, we can make it even more efficient by taking uranium-238, again, the stuff that's no good in reactors, and lining the fusion chamber with it so that the spare neutrons will cause fusion, or will cause fission in U-238. Remember, in our table, U-238 is fissionable by fast neutrons. Not that fissionable, but we can still get some more energy out of it. Fusers, I'm not sure about. I need to read more about how that works. I know that from what I know, a fuser is an electromagnetic thing that will let you get a little bit of nuclear fusion with a whole lot of electricity, but it's not something that you'll ever get a net amount of energy from. So I want to pivot now. People have asked a lot of questions here. We'll come back and talk about fusion stuff, but I want to talk about medical physics now. That was Danielle's question from a while back, which is an entirely more peaceful approach to this. And it's actually a really cool story. So it turns out in think about how a medical X-ray works. Um, in an X-ray, um, so here is you. X-rays come in. Some of them pass through you. Some of them are absorbed. And you get over here basically a shadow. This means that your body had to absorb quite a lot of radiation for to get kind of a cruddy image because it's just a shadow of where your bones are. A CT scan is just this same sort of shadow, but done from all angles with a complicated computer algorithm that reconstructs the 3D image. But it would be great to make an image of somebody if you could make the person emit the X-rays. And so the way to do that, consider instead a process where you have a person drink a radioactive thing, and for that chemical to migrate to regions of interest. So say, for instance, the canonical one, the one that I'll talk about first, is bone injury. And then we can detect, I can spell, detect radiation just from the injured or diseased region. That's a lot better for a person, right? Because now instead of bombarding the whole person with radioactivity, with radiation, you can have radiation come only from the injured spot and get a much better picture. And you can also kind of learn about the chemistry inside a person. I should say that chemical migrates. So this is done. It turns out that one of the common fission reactions, and I need to Google a particular isotope here. Give me one moment. Okay. So in nuclear fission, you can have uranium-235. Remember, uranium-235 goes to 2 smaller nuclei. So in a fission reactor, an example of one of those is molybdenum 99. Molybdenum 99 is not super interesting, but its decay chain really is. So one of its decays, well, its main decay, is molybdenum 99 goes to technetium 99. I'll write them actually in the more nuclear physicsy way. This has a half-life of around 3 days. But remember, we've talked about ground states and excited states of atoms. Did you all do that in class? This is an excited state. I'm going to do this, write this with a star. This is an excited state. And then the excited state of technetium decays to the unexcited state of technetium with a half-life of a few hours. I should note that this is, and this is the important part, a gamma decay. So it releases gamma rays. So here's how the process works. And Danielle, please ask questions if you've got them about this. In nuclear reactors, in specialized nuclear reactors, they fission uranium-235. And in doing that, they produce a whole bunch of crap, but they chemically extract the molybdenum-99. That molybdenum-99 has a half-life of about 3 days. So very quickly, they ship it around the world to hospitals. And those hospitals keep the molybdenum-99. It's constantly decaying to technetium-99. And they chemically separate the two. So they do a chemical reaction on the molybdenum to extract the technetium. And that's this technetium-99 star, the excited state. They give that then to patients to drink. So patients are drinking this. Yes, Danielle, that's the radioactive tracer. But technetium-99 does a funny thing in the body. The thing that makes this work is that technetium-99, actually all of technetium, is scavenged by osteoclasts. Excuse me, osteoblasts. These are cells that construct bone. And they migrate to regions of bone damage. So you drink technetium-99, it is radioactive, it'll decay over a few hours, and then your body picks it up and puts it anywhere where bones are damaged, because your body is trying to rebuild bones. And then anybody who takes a gamma ray picture of you will see gamma rays coming more intensely from regions of damaged bone. And this isn't just like a shadow, right? Like an X-ray is just a shadow. You have to bombard someone with X-rays and you get only a silhouette. Here, you get a very clear image. You get gamma rays coming out of places where bones are damaged. And this is the best way we have to find things like bone tumors or bone fractures. My mother actually had one. She has an artificial hip, and she was having a lot of pain in her hip. And honestly, the surgeon had kind of botched the operation. And he gave her one of these scans to see if her artificial hip was infected. It turns out it wasn't. It turns out it was like a way more mundane problem. And she didn't really need the extra radiation of this technetium bone scan. But this was kind of like this is the best test we have to see if your hip is infected or not. It turns out you can also bind technetium to other atoms if you'd like to investigate other kinds of body chemistry. So you bind it to some other molecule, and if you know the biological activity of that molecule, you can then see where that molecule has gone in the body because it's bringing the technetium with it, and then gamma rays come out of it. So yes, Danielle, that's how that works. What kinds of tracers are given to patients with other diseases like lupus? You may know more about this than me. I am not at all a biologist. I know that one because my mom had one, right? But the radioactive tracer may be the same. They may use technetium for those as well. What's different is the biologically active chemical you bind it to. So you take technetium-99 star, you attach it to a biological molecule that will go wherever you're interested in, and then you have an image of where those biomolecules have traveled. I am not super sure of how the biochemistry works for lupus, but I'd love to hear if you have wisdom on that. Ah, I see. Yeah, if you have, come back and tell us, Danielle, if you hear like what what tracer was used or and what its bioactivity is. And they sometimes use things other than technetium. Like this is one example. It's nice because it's a this is a very fast decay, right? So this happens in 3 hours. So most of the radioactivity may come out in the hospital, but technetium 99 itself has a half-life of like 200,000 years. So it's not very radioactive. It's not going to hurt you further, and you'll basically pee it out. um, yeah, if you find out, let us know because that would be a really interesting thing to talk about, Danielle.
So they would only be able to take the picture in the 3 hours in which it's decaying?
Yes, yes. It decays exponentially, so it's getting weaker and weaker and weaker. But yes. Um, so they have you drink the stuff, give it 15 minutes or whatever to make it to your bones, and then they take their picture. And that's good because they don't want you to be radioactive for a long time, right? you know, they want to send you home and let you do stuff like that. And there's another one. Um, does anybody here know the biological activity of iodine?
It goes in your thyroid.
Yeah, yeah, the thyroid uses it. And if you have someone with either hyperthyroid, where their thyroid is too active, or they have a condition where their thyroid is there's an immune reaction to the thyroid and you want to like get rid of your thyroid because your immune system is trying to murder it and making you miserable, you can have someone drink radioactive iodine and it will go to the thyroid and then in weeks after decay and kill your thyroid. Um, I have a friend in Arizona who has a disease called Hashimoto's disease, which is an immune reaction to the thyroid. And so she drank radioactive iodine, killed her thyroid gland, and now she takes thyroid hormones to replace its activity. But that has a half life of like a week or two. So you probably shouldn't, like be close to people during that time. So she had to, you know, like couldn't give her mother a hug while she was waiting on her thyroids to get toasted. So that's another use of nuclear medicine. Ah, Ava asks about iodine combating radiation. Yes, so iodine, I believe it's iodine 131, is a big component of, it's a big fission byproduct. So in a nuclear explosion or in a nuclear disaster like Chernobyl, one of the longest lived health effects is actually contamination with radioactive iodine. I may have said something that wasn't clear a bit ago. Iodine 131 has it. Yeah, okay. Its radioactive decay half life is 8 days. I wanted to make sure that wasn't its biological half life, how long it takes for you to excrete it. So in Chernobyl, when that reactor went pop and scattered basically all of the fission byproducts out to the four winds, that iodine 131 got everywhere. It was picked up in Sweden. And the danger there is that if you drink a lot of it, it will kill your thyroid. But if you drink a little bit of it, it will go to your thyroid and then over those 8 days decay and cause genetic damage to your thyroid, which can lead to thyroid cancer. So that's why thyroid cancer is like, that's the biggest public health consequence of some of these nuclear accidents. But if you know this has happened and you eat an enormous amount of ordinary iodine, like not the radioactive isotope, I don't remember what the stable one is, uh, your body will be completely saturated with iodine. Your thyroid will scavenge anything it wants, and most of it will be urinated out. So if you ingest iodine 131, the radioactive stuff, your body will be completely full up on iodine, and your thyroid won't absorb much of the radioactive stuff, and it will be excreted just because your body is super saturated with the stuff, um, just like the ordinary iodine. So um, this is why like iodine tablets are used as a nuclear radiation or a nuclear accident response thing. Any other nuclear radiation questions or nuclear physics questions?
I have one.
Sure.
Um, so speaking like army wise, if I were to take like the MO99 isotope
Hmm.
and I were to put it on, this is gonna be a little violent, and I'm sorry, but it's my
For
profession.
people in the army, yeah.
um, and I put it on a bullet or in a bullet, and I wounded someone like an enemy soldier, and they went back to a place where they were hiding out or something, say it was a
Mm.
terrorist. Could I have a plane equipped with one of those cameras that sees those gamma decays fly over, and would I be able to find where that person is, or would it not be enough of a dose?
It would likely not be enough of a dose,
Okay.
because the gamma rays will travel a fair distance in air, but not that far, not to an airplane. But things
Okay.
like detecting telltale gamma rays of particular energies, this is a way to like they scan cargo containers for nuclear materials, and that's one of the ways it's done.
Okay.
Um,
Okay.
so yes, those sorts of radioactive tags are that's absolutely a thing people do, but it's shorter ranged and you need more of the radioactive substance. Um, but yeah, that's a creative use of this. Um, actually, Ava and Matthew, it's something simpler than that. So if you remember your chemistry, iodine is a halogen like chlorine, and so chlorine in is kind of a rare thing, but chloride as in ion form is pretty common. So sodium chloride, I have some in my cabinet, right? And it turns out that the most common, so that's called a salt. And if you want to have a stable chemical that has a halogen in it, sure, see you, Isa. Enjoy your vectors. If you want to make a stable chemical that has a halogen in it, you want to bond it with a something on the left side of the periodic table. So potassium iodide is the most common salt with iodine in it. So when you say potassium tablets, the potassium is just what you put with iodine to make potassium iodide, which is a stable salt. Um, there is a radioactive isotope of potassium. It turns out it's natural potassium 40, and it's not that radioactive. It has a very, very long half-life, but it is used in the radioactive dating of rocks. So potassium 40 is one of the ways that we know how old the Earth is. Anything else anyone wants to talk about? I will hang around after class if anyone wants to. Where can you find them on YouTube? I will send out the links. Um, they are, again, I was late last week um, doing this just because I was sick, but I have all of the videos. They should all be up on YouTube, and I'll do this one and then mail out the links. Um, so enough radiation to get cancer is actually a really funny thing because it turns out all we can say is probabilities, that a certain amount of radiation exposure has a certain risk. As best we can tell, it's linear, but nobody really knows for really low doses. But yeah, people like to joke about the banana equivalent dose. Um, there's a great XKCD. Uh, so if you go here, one of the low doses that's marked here is eating one banana, zero point 0.1 microsievert. Um, I ought to note that that is zero point 0.1 microsievert is 1 millionth of the lowest dose clearly linked to increase cancer risk, according to the table. There was one question way back about from Tige about how do you make what's a fusion bomb? What is a thermonuclear bomb? So Tige, if you're still here, I have a diagram of one of those. Where is it? I thought I did. I guess not. So a thermonuclear bomb, a nuclear fusion bomb, is just so in what I showed you earlier. The Swan device is kind of a modern small fission explosive, like a suitcase nuke. But in a fusion bomb, you're actually getting energy out of the fusion. The fusion is actually a primary source of energy. And so you use something like this picture, and put it inside of a case that has a very dense exterior. And that dense exterior contains the pressure, at least for a moment, and uses that pressure to compress lithium deuteride. So that's something that you can have undergo nuclear fusion. They use lithium deuteride, I believe, because that much tritium would be very, very expensive. You can also use tritium. I think tritium is better, but tritium is very difficult to produce because you have to basically bombard deuterium with a whole lot of neutrons in a reactor to make it. So you have an ordinary fission explosive. It goes pop. It produces an enormous amount of heat and pressure. That heat and pressure compresses lithium and deuterium, which are the fusion fuel. And that fusion fuel provides much of the energy. But you can go even further beyond that. So I said that the whole thing is contained inside a case made out of a very dense substance. And if you are a country that's interested in nuclear weapons, then you're probably enriching a lot of uranium. So enriching uranium, remember, you're separating the U-235 from the U-238. U-238, you can't make a reactor out of it. It's not terribly fissile, but it's super dense. So it is a very handy thing to make the case around a thermonuclear fusion bomb out of. But if we look at the fission cross sections for slow neutrons, that's basically zero. For faster neutrons that are what you get from a fission reaction, 0.3 is reasonable. But then the even faster neutrons that come out of nuclear fusion are even more likely to induce fission in uranium-238. So what they do is they make the box called the tamper around this whole thing out of depleted uranium. And then all of the neutrons that come streaming out of the fission reaction then strike this depleted uranium and cause... It's not a chain reaction, right? You can't make a chain reaction in uranium-238, but you can still turn all of these extra neutrons into even more energy. The problem is this produces even more radioactive byproducts, right? Because you've got, you're fissioning uranium and those pieces are going to be radioactive. So the very largest thermonuclear explosives they call them fission, fusion, fission explosives. You have a fission reaction that starts the whole thing. The heat and pressure induce fusion in lithium deuteride, and then all of the neutrons that come out of that can induce nuclear fission again in uranium-238 that is there just because it's super dense, but also a way to turn those neutrons into energy, if you want to do that. Often people making fusion explosives don't want to do that because they don't want to produce extra radioactive fallout. Does that answer your question? Yeah, it is, and it's a shame that so much interesting physics is tied up in warfare, in this thing that would be absolutely horrible if it ever happens. I don't know. I would like to teach one. It would be pretty cool. I would be more organized than this because I'm this is kind of my side project of teaching 361. But I don't know. But the best, if you all want there to be a nuclear physics course, the best thing that you could do would be to get people who say they would take it if it were offered. If you and your classmates would like that to happen, like get a list of names together of people who would take it, and give it to me or give it to Jenny Ross, and that may make it happen. There's a ton of really cool stuff we haven't even talked about, and that's just what I know. I'm not a James. Oh, would taking 531 thermo be a good idea? Um, James, so you're a physics major. Are you a double major? I forget. Yeah, comp sci. Um, yeah, so taking 531 would be a good idea. So you're good at math. Some of the stuff in 531 can be a little bit mathematically challenging, but we have a problem in our physics department, and part of that problem is that most departments have basic thermodynamics early in your academic career. We do not. I wish we did. Um, you're a second semester sophomore, is that right? Yeah. So there's a whole lot of stuff in physics and engineering that makes more sense if you understand some thermo. So I would go ahead and take it. If it's offered in the fall, it'd be a good time. Yep, thank you.